Okay, so we have learned. Let me close the door here. We have learned a lot of different types of integrals over the past week or so, and I just kind of want to summarize what they are, explain the connections, and I hope it'll help you kind of see sort of the general patterns of what's going on here instead of having to memorize a whole bunch of isolated things. So I first want to talk about line integrals, and then I want to talk about surface integrals. So I'm going to talk about line integrals first. So line integrals. Okay, so when we first talked about line integrals, we had some curve here. It could be in the plane, or it could be in 3 space, or it could be in 4 space even. 5 space, 6 space, whatever. But I'm going to draw it in the plane here. And let's say this curve has parameterization r of u. So I'm going to use r of u instead of r of t because when we get to surface integrals, I'm going to be using u and v. So we have a line integral, so we have a curve that has parameterization r of u. Okay, and if we have a scalar field, if f of xy is a scalar field, which I'm just going to abbreviate as scalar field, we can define its line integral over this curve. Okay, remember scalar field means its value is not a vector, its value is a number. And we talked about one motivation here would be maybe f of xy is sort of the density, the mass density along this curve here. And then the line integral of f along the curve would represent its mass, like the mass of a wire lying along a curve like this. So the line integral of a scalar field is going to be denoted like this. We put c down here, like if c is the name of the curve, we put c here, d little s. Okay, so actually let me use some different colors here. So f is the scalar field, and then we're going to do d little s. Okay, and so what this means, f is the scalar field, and the ds means we are integrating with respect to arc length. It's going to be the density times a little bit of arc length, and that's going to give us mass, for example, if f represents mass. Okay, and then we realized, okay, we have these things called vector fields. So if f of xy is a vector field, VF for vector field. Okay, and again, there's several different interpretations for what this could be physically, but one interpretation is that f is represents force, and so the line integral of f over this curve is going to represent the work done. Now, for this, the work done in moving an object from there to there is going to be negative the work done in moving an object from there to there. So then something called the orientation of the curve matters, like the direction that the curve travels. So if this is the parameterization, the direction of the curve matters when we think about doing something like the line integral of a vector field. Because again, going from there to there, the work done to move an object from there to there is going to be negative the work done to move an object from there to there. Okay, and so for this, we're going to have the line integral c. We're going to have our vector field f. So this is the vector field, and I'll move out of the way here. I don't know if I'm blocking the camera now. And then we're going to dot it. So f is a vector field, and then we're going to dot it with ds. And this right here is a tangent vector. Tangent vector to the curve. That's the tangent vector to the curve. And so what this is, f dotted with a tangent vector to the curve, that's like the work done by the force field F to move a particle a small distance along the curve. Okay, so let's actually see how we practically compute these things. So for our parameterization up here, let's say our parameterization, we have 0, less than or equal to u, less than or equal to capital T. Okay, then practically speaking, this is going to be equal to the integral from u equals 0 to u equals t, our scalar field evaluated at the parameterization, and then we're going to multiply by the magnitude of the derivative, r prime of u du. And down here, if we want to do the line integral of the vector field, this is going to be equal to the integral u equals 0 to t. Our vector field f evaluated at the parameterization r of u, and then we're going to do dot. We're going to dot this with r prime of u du. Okay. So these are the line integrals of these are line integrals of scalar fields and vector fields. Okay, so now let's see what happens when you look at surface integrals. So now I want to look at surface integrals. Okay, sorry about that. So now I want to look at surface integrals. So now, let's say we have some surface in three-dimensional space here. We could think about a surface in two-dimensional space, but that's just going to be a region in R2. So we don't typically think like that. So we're going to have some surface in two-dimensional space, or sorry, three-dimensional space, or it could be in higher dimensions as well. But again, we just think about surfaces as being in two-dimensional space. But now we have some vector parameterization, r of uv. Okay, and just like u over here kind of tells us like where we are, so I could have, you know, maybe this corresponds to r of 0, or sorry, let's say r of 1, and maybe this corresponds to r of 2, so I can associate this point with u is equal to 1, and I can associate this point with u is equal to 2. In a similar manner, the parameters u and v give us coordinates on the surface here. And then if I say look at maybe these lines right here represent fixed values of u, so u is equal to 0, u is equal to 1, u is equal to 2, u equals 3, u equals 4, then if I sort of fix u to be 0, and I let v vary on its domain, it's going to trace out this part of the curve here. If I come here to say u is equal to 1 and hold u constant at 1, and let v vary on its domain, it's going to go along that curve there. And this is an r, not a v. Okay, and then here, maybe these represent, you know, constant values of v. So maybe this is v is equal to 2, and this is v is equal to 4. So if I hold v is equal to 2 constant and let u vary, it would trace out that curve there. Okay, so now I can think about the line integral of a scalar field. Okay, so the line integral of a scalar field, well, first I can think about, we first did the surface area. And I should have mentioned over here, we first did the length of the curve here. Remember the length of the curve, we figured out how to find the length of the curve. The length is given by the integral over the curve C, the integral from u equals 0 to t, the magnitude r prime of u du. Okay, and what we did in class was that we noted that approximately the area of that little coordinate patch there, like if that, if I pick a value of u and v, the approximate area of that little coordinate patch right there, which I'm going to call delta A, is approximately going to be equal to the u derivative of r cross the v derivative of r, that magnitude, times delta u, delta v, where I'm saying like evaluating the derivatives at that point, or really any point in the square there, or in that little coordinate patch there. Okay, and then we saw, okay, well, what about if I have a scalar field, f of x, y, z, and f of x, y, z represents, for example, the mass density of this surface. Just as one way to motivate what the surface integral of a scalar field will be. Well, I can do the surface integral of a scalar field. Let's call this surface S. So we do two integrals because it's a two-dimensional thing. F, let me use different colors. F This is the scalar field. Times ds. And this represents the surface, just like this represents arc length, this represents the surface area of a small patch. A small patch being something like that. And of course we let delta U and delta V go to 0, and the patch goes, the size of the patch goes to 0, and we get a better approximation. Okay, so now let's think about the line integral of a vector field. Okay, now here's where we're going to have a difference. So if we compare these things, the line integral of a scalar field and the surface integral of a scalar field, they're very similar. They have very similar interpretations in mass and that sort of thing. The formulas here look very similar. Purple scalar, blue arc length, purple scalar, blue surface area of a small coordinate patch. But now, when we want to think about the surface integral of a vector field, our interpretation is going to be a little bit different. So here, our vector field, we're thinking about our vector field as being, we want to know like the portion of our vector field that is parallel to the curve. Over here, when we do the surface integral of a vector field, we actually want to know the portion of the vector field that is perpendicular to the surface. Okay, and the reason is because both of these arise in kind of different ways, though there's reasons to do both of them. Okay, so what I mean by that is, remember, one of our motivations for the surface integral of a vector field, maybe f represents something like, maybe f represents the big F. F represents something like velocity, like fluid flow velocity. And I want to know how much fluid is flowing through the surface at a given time. Well, what I'm going to do is I want to look, the only part of F that is causing fluid to flow through the surface is a part of F that is parallel to the normal vector to the surface. Because otherwise, if I have like a surface like this, and I have fluid flow going in this direction, the part of the vector field that is parallel to the surface is just it's not going to cause any fluid to go through the surface, it's just going to cause it to go tangent to the surface, but not go through the surface. Okay, so it's only the part of the vector field that is parallel to the normal vector to the surface. And so if I do the line integral of a vector field, it's F dotted with ds. Okay, and again, this is a vector field. But notice this is not going to be like a tangent vector to the surface. That's even a little difficult to define. It's not going to be a tangent vector to the surface. It's going to be normal vector, or perpendicular to the surface, I'll say. Okay, but then in terms of actually computing this integral, we're going to integrate over the parameter domain D. So I have my parameterization R of u, v. Like over here, u goes from 0 to t. Over here, u and v are going to lie in some parameter domain in R2. We're going to evaluate f, our scalar field, at the parameterization R of u, v. And then we're going to multiply by the u derivative of r crossed with the v derivative of r dA. Sorry, let me do that in blue to keep this consistent. So this is going to be equal to the u derivative of r crossed with the v derivative of r dA. Okay, so down here for the line integral of the vector field, what we're going to do, we're going to look at the integral the surface integral of the following scalar field is going to be f dotted with the outward pointing normal vector, and then times, actually, so let me write it like this, dotted with the outward pointing normal vector ds. Okay, so notice this is a scalar field. I'm doing f dotted with in. That gives me a scalar field. Okay, in is a normal vector to the surface. And now, is where you might remember, we have to talk about the orientation of the surface. So if I have a surface, if I have a surface like this, imagine my hand's kind of like describing a surface. If I have a surface like this, the outward pointing normal vector I could either define to be this way going up or this way going down. Okay, so we just have to pick a way. And the way that we normally pick, there's normally obviously sort of an outer pointing normal vector. If I have a sphere, if this is a sphere, the outer pointing normal vector is going to be something like this. But if I just have some random surface like this, it's not so clear what should be the outward pointing normal vector. The physical situations will tell us what the obvious choice for the outward pointing normal vector is, but we normally just take in. I'll write a little formula up here. We normally just consistently choose in to be equal to the u derivative of r crossed with the v derivative of r divided by the magnitude of the u derivative of r crossed with the v derivative of r. And if you did the cross product, if you exchange the orders of the factors in the cross product, you would get the other vector. So if RU cross RV gives you this vector, RV cross RU will give you this vector. Okay, now if we just kind of plug in what we're going to get, so n is equal to this formula. So this is a line, this now is a scalar field. So if you plug this into here, you're going to get f dotted with this normal vector, but then when you multiply it by this factor here, the magnitudes are going to cancel. And so what you end up with is the following. Might run out of room here. This is the line integral uv in the parameter domain d, and I'll get out of the way in just a second. Is going to be f evaluated at the parameterization r of uv dotted with the u derivative of r crossed with the v derivative of r times dA. Okay, and that's the way that we compute the line integral of a vector field. Okay, so again, the amount of new integrals that we're learning has grown significantly. We've been doing line integrals, we've been doing integrals for a while. Then we did integrals of, double integrals and triple integrals. Now we're doing calculus on curvy objects, calculus on curves, calculus on surfaces. And so it's very natural to want to do calculus on those objects, but we just have to figure out how those things are defined. How they are defined is based on their motivations from how they're going to be used, and then we have to figure out how they're computed. So this right here would be how the line integral of a scalar field is kind of defined almost, and this is how we compute it. Okay, so that's it for this video. I'm going to try to make another video where I explain we've learned several different theorems. Green's theorem was the fundamental theorem of line integrals was the first one we learned. The second one we learned was Green's theorem, and then we just recently learned Stokes' theorem, and I also want to talk about the divergence theorem as well.